Dear colleagues, we would like to welcome you to the poster session on Thursday, 25th of July, where we will present our research about the application of language models to the algebraic topology. In mathematics, machine learning demonstrated remarkable abilities in various tasks such as finding counterexamples, generating formal proofs, and many more. We, inspired by these recent advances in this field, decided to apply these methods to algebraic topology, particularly to the problem of homotopy groups of spheres. Computing homotopy groups of spheres stands as one of the most challenging problems in topology and mathematics in general. Over the past century, the complexity of this problem has spurred the development of numerous sophisticated mathematical techniques. The computational aspect of this problem was first approached by Brown, who proved that this group is finitely computable. However, the algorithm presented was shown later to be super-exponential. Current frameworks still require a lot of computations, but more importantly, they do not give any insights into the homotopical structure, since they output only the group as an answer and not its generators. Notably, they are based mostly on algebraic topological methods. We take another route. We apply a combinatorial algebraic tool known as Wu's formula. Using this approach, we would be able to recover generators, and more importantly, objects we are going to work with will have computer-friendly representations. The key object we're working with is free group. It is a group of all possible words over the set of generators x1, xn, and their inverses, with only the rule that xi multiplied by xi inverse and vice versa is identity. Next object is the normal closure of the generator. Basically, it's the subgroup of the free group consisting of words such that if we remove xi from it, then the word would collapse to the identity. We are going to be interested in the intersection of these subgroups, and notably, commutators, the definition you can see on the slide, are the example of words that can simultaneously lie inside several normal closures. Here is Wu's formula. Note that x0 is the multiplication of all x's. Basically, this formula tells us that to recover a homotopy group of the two-dimensional sphere, we need to find such elements from the intersection that are not commutators of a certain structure. These commutators of the certain structure are called trivial elements, and elements that are contained in the numerator and not in the denominator are called non-trivial, and we are interested in finding them. However, distinguishing trivial and non-trivial words is a very complex task, as hard as computing homotopy groups itself. There is no algorithm or just general instructions on how to do it. One should come up with a sophisticated method for every particular word. So, we decided to focus on generating elements from the numerator, or simplicial cycles, as a proof of concept. However, to avoid the degenerate behavior of the model, generating only trivial words, we are going to avoid using information about the denominator. It turns out that if we consider incomplete intersections, then they would be equal to these commutators of certain structure. So we decided to formulate the problem as follows. How we can learn the complete intersection? By having dataset for words from the incomplete intersections. We propose a new interesting computational problem, how we can find elements from the complete intersection of algorithmic datasets having information only about the incomplete intersections. We develop classic cost-based optimization methods as well as language modeling-based approaches to solve the task. Moreover, empirical superior performance of language models on this task shows interesting insights about learning capabilities of the transformers. We model the free groups as a language with generators and their inverses being single tokens. The first baseline we used is random search from incomplete intersections. It is interesting to compare language models with this method to find out whether transformers learn something else than just training distribution. Other baselines are cost-based optimization methods. As a cost, we use the sum of some sort of distances to the normal closure. We can remove the ith generator from the word and look at the remainder, and say that the length of the remainder would be the distance to the ith normal closure. Interesting representative among these methods is greedy. These methods generate word token by token, trying to greedily minimize the cost on every iteration. As for the language modeling, we use GPT-2 and trade it in the classic next token prediction fashion in two regimes. We call the first regime ignore. We use only words from the dataset and not the information about which normal closures contains this given word. And the second regime is prompt. We use this information as a prompt, so the input sequence in this case is special symbols denoting in which normal closures this word is contained, and then some special delimiter and the word itself. To compare methods, we use the matrix called the completion ratio. It is the ratio of prefixes of a certain length that the model is able to complete so that the resulting word is contained in the complete intersection. On the slide you can see the bar plot comparing the completion ratio of proposed methods with different parameters of n. It can be seen that the language models outperform random search, which means that they learn something more than just the distribution from which the random search is sampling. Moreover, prompt outperforms other methods on n equals to 4 and 5. Greedy method has an exponential decrease in performance from n to 3 to 4 and 5. Other cost-based methods have around 0 performance on this task. Here's the training dynamics of completion ratio for ignore and prompt methods, as well as the negative baseline, which is the language model trained on the trivial words only. As it was expected, it approaches almost ideal performance. One can note that ignore method stagnates after a certain time and prompt in contrast continues to learn. In conclusion, we evaluated machine learning methods on the task of generating simplicial cycles and proposed novel computational tasks. We implemented classical as well as novel language model-based approaches to solve this new task. The resulting language models are more scalable than proposed baselines. In the future, we are planning to employ more sophisticated tokenization scheme to increase performance and reduce the computational burden by compressing words, and approach our ultimate goal, sampling elements from homotopy groups of spheres, by distinguishing trivial and non-trivial words. Thank you for your attention.